I'm by education a theoretical physicist, and I hold a chair for theoretical physics and its application in the life science at the University of Freiburg. And what we are doing in the group is that we, on the one hand side, develop mathematical methods to analyze time series or dynamical process data from the life science, and on the other side, apply it in collaboration with biologists and clinicians to real-world problems. The basic idea is that in the theory of dynamical systems, there is a field where people investigate systems that have two stable states, and they look at the condition under which the system switches from one state to the other. This has been applied to a lot of chemical and physical systems, and the idea here now is to transfer this concept from physics and engineering to psychiatry, because these two stable states could be something like healthy mental state and the diseased mental state. And the special thing in this theory is that they not only investigate models that do this, but they also have invented signatures that can be extracted from real-world measured data as a kind of early warning of the system. This is something that has to go hand in hand. Yeah, so for example, if we build a model, this model will show certain time scales in which things are happening. In case of mental disease, if you experience a stressor, how fast will you relax back to a normal state? And to figure out these timescales, which in the models are just parameters, of course, we need empirical data to get a feeling whether the timescales is minutes, hours, or weeks. So there have to be data first, and we already have data. And based on this, you can build a very simple model. And then based on this simple model, for example, make suggestions for the improvement of the design of then again clinical studies. In the group of Raphael Kalisch, they have in Mainz performed certain studies, the MAP study, the life stress study, and there are, for example, in one of these studies for 4 weeks, every day 5 times in a certain random, that people do not get used to it, certain random manner, people are asked to judge their mental state by fixed criteria, and then they are asked how many daily hassles in very different fields, from family stuff or work stuff, even financial stuff. And these data are already existing, and we are now building models to figure out whether we can somehow reproduce the dynamics in these empirical data. This is a very, very important point, because from a cross-sectional study, meaning you take a lot of patients or subjects and ask them once how they behave, of course you cannot infer dynamical behavior. And what we are doing in biomedical terms, it's called longitudinal studies. In my word, it would be dynamical or time series data. We really follow single subjects over longer times. The goal, of course, is, and this is a very ambitious goal, is to develop these models or signs, early warning signs, for the individuals, so not just for a cohort where we can say with a probability of, but to make this specific. How close we will get to this goal is one part of DYNAmore.
The aim is basically DYNAmore has to have an effect really in the real world. And so on the one hand side we have Jensen's model, on the other hand side we have the real world. The question is, how do we connect these two? And when I say real world, this means typically problems like missing data. For example, participants won't sometimes fill out questionnaires every single day, so values will be missing. But for feeding this into the model, there cannot be missing data and such problems. So you have to do something about this. And one idea was that artificial intelligence techniques are currently quite popular and quite successful. And so we thought, could we use such techniques for solving our problem? And what we did so far really was training artificial intelligence techniques for learning the temporal patterns of what participants are answering in questionnaires, and then the AI can predict what would be the response of the participant if the response is missing. And so in the end we make it nice and clean data to feed into the model. You have really different kinds of data, but also it's a huge number of characteristics that we have for each participant. What is the number of parameters the model will be able to take? Yeah, maybe we can do 5 or we can do 6. We are starting with hundreds of measurements, so we need to boil down all this heterogeneous data. And then we said, okay, let's turn again back to our artificial intelligence system to find some underlying structure in these hundreds of measurements, a few really salient dimensions, and after we have identified these can again be fed into the model. I mean, one way would be to explicitly say, okay, this is our gender factor, but we want to work hypothesis-free. And so if the AI will find such gender patterns, then we will take them into account. But if we find that there's a gradual gender difference, we will model this gradual gender difference. And this helps us for not encoding any cliches or something like this into the model.